Let's implement one more function, remove a function. So remove a function takes the position of the node and then the node will be removed from the list. So here is just a very simple test code for that. Once remove is implemented, assume that then beginning with the list M, we append the 5, 7, 9, 2, then they are in 0, 1, 2, 3 position. So if we remove a 0, means that we remove data at position 0, then 5 is removed, so that if we get position 0, then 7 is a position 0, 9 is at position 1, and 2 is in position 2, the like. So from there, if we remove 9 from the list, then at position 0 we will have a 7, and then 2 will be now at position 1. So we are going to implement a remove a function that way in list.h file. So remove a function should be void return, and then position is provided. Let's implement a remove a function. In CPP implementation, remove a function. First, let's validate the input parameter position. So to remove a node at a given position, position should be 0 or positive. And then position, maximum position should be one less size of the array list. Assume the array, then the size and the last index is one difference. So similarly, in the list, the valid input parameter pos should take this one. And you may wonder why we do not check if list is empty or not. If the list is empty, remove is meaningless. Actually, this assertion condition includes the empty condition. When the list is empty, size is 0. So meaning that valid size should be less than 0. It should be negative. But here we check position positive or 0. So if a list is empty, so assertion will always fail. So it is included. So let's implement a list function. Once list remove a function, if remove is successfully done, we will decrement the count, the number of elements in the list. So to visualize the remove a function, to find how many cases we need to find, we need to process, let's draw a picture for that. We have a list variable which has a head and the tail pointer, and then nodes are linked together. Assume it has a 4 data. Then this is a head node and this is a tail node. Between nodes, a node is pointing to the next one, and so on. The very last one has a null pointer. So let's find out how many cases we should take care. So remove what will be on the left hand side, what will be on the right hand side of the node to be removed, and then when is such case. So if we have only one single node in the list, so only one single node, when count is 1, if there's only one single node, then the node to be removed, the left of it is a list object there, and right hand side is nothing. So that's when count is 1. Another case, if we remove a node at position 0, so we have more than one node, but we are going to remove the very first, the very head node, then left hand side is list, right hand side is another node. And then if you can remove a node between two nodes, so we have a node on the left, another node on the right, then position should be at least 1, greater than 0, and then the position should not be the very last node. The very last node position is a count -1, so position should be less than that, up to the second to the last one. Then we are going to remove a node between two nodes. And then the last case is that left hand side is node, right hand side is nothing, which is the very last node. The very last node, there's nothing on the right. So if a position is the same as count -1, then we are removing the very last node. So we have 4 different cases that we need to consider in implement the removal function. So let's implement one by one. So first case, if size of the list is 1, so that's the only node. The only node we are going to delete. Then after here is the only node. The only node is pointed by head pointer, so we need to free the memory pointed by head. Then head and the tail of the list is null. We have removed the only node. Else, if position is 0, which means we are going to remove the very first node. So the very first node we are going to remove. Then this is actually exactly the same operation, pop operation of a stack. Pop, assuming that green part is a stack variable, then you have a top of a stack pointer which is pointing to the very first node, which is top of the stack. So if you do pop, what you do is we set bypass to the second node and then free the memory. So pop of the stack, what we did is save the address to be removed, which is pointed by head variable, and head we go to the next link, so we bypass the first node. So that's a second case. And then third case, I forgot to give if. In third case is that position is greater than 0 and then position is less than count -1. Then we are removing a node in between two nodes. So here, deleting between two nodes, it's a little bit complex process. So let's try to look at the picture and then find the operation needed. So first node is index 0, 1, 2, and 3. Suppose we are going to remove a node at position 2. So this node, we are going to delete that. Then deleting means we set a bypass link from node 1 to node 3, go directly in bypass second one. That is how to effectively remove node 2 from the list. But to do so, let's figure out what operation we need. Setting the bypass red link here means that in this variable at node 1, we need to write the address of node 3. So this variable is a link member of node 1. So let's assume that variable left, it's a pointer left, is holding the address of node 1. The reason why I'm calling left is left of the node to be removed. So anyway, if we find the address of the left node, then writing something into link member is a left arrow link. So this is the variable here. So in this variable, we need to write the address of this one. So address of this one is stored in link member of a node to be removed. So what is then variable name of this one using left is left arrow link. If I do left arrow link, then we are referring to this variable, but the value stored in this variable is address of node 2. Then another arrow link is the variable here, and this variable is holding address of node 3. So setting bypass link. So setting this bypass link means left arrow link assignment, left arrow link arrow link. So that's the operation. So here the main thing to implement the case 3 is find the value of left, which is address of left node. So to do so, what you need to do is that to find the left of 2 is beginning from head. Head has address of first one, so we need to move through the link one less pos times. If pos is 2, one less pos is 1. So once from the head, just go through the link once. Then in this variable, the address of node 1 is there. So what we need to do is beginning with the head. So we need to go through looping, jumping through link. Beginning with the 1, pass minus 1 times, loop this many times, pass minus 1 times to loop, and then left is updated by left link. So we follow through the link. We're jumping through the link by pass minus 1 times. Then at the end of the loop, left has address of the left node to be removed. Then left link should be left link link. Then we set the bypass link. This formula we figured out in this picture. But if we set the bypass link, the address of this node is gone, so we save the address of the node to be removed, that is in left link there. So once we set the bypass link, free the memory. That's what you need to do. And then the rest is the remaining case is we are going to remove the very last node. Removing the very last node means on the second to last node. So let me change. So second to the last node, in link member we simply set null. Then there's no more after that. So we need to do set null to the link member of a second to last one, and then the tail pointer should be updated to that one. So we need to two things. So tail pointer should be updated accordingly. So here what we need to do is find the left of the last node. So finding left of some position we have already done in the previous case. So let me copy code for that. So now in the last case, pass is the last one. So by doing pass minus 1 times of jumping through the link, now the left is address of the very last node after removing the last one. So second to last node. Here the link should be null pointer, no more after that. Of course, we need to free the memory. The very last node is freed. And then we set the link of the second to last is null point, and then tail pointer should be updated by the left node address. So this is the implementation of a remover function. So let's verify the code. So in main program we did the very small minimal testing there. So here as we have 4 nodes, we remove one by one. Here we remove at position 0 and then remove at position 1, not 9. So remove is by the position. So the one at position 1 is removed, then only 7 and 2 are left over. So that's a minimalistic testing code. Compile the program, run. So minimal testing is successful. So we will do in a later video the comprehensive automated testing.